Hi, my name is Shivam Patel, and my project is on single-pulse laser ablation simulations of femtosecond and nanosecond lasers on an aluminum lattice in a vacuum. So my abstract: simulations of laser ablation on a aluminum lattice in a vacuum are created using large-scale atomic/molecular massively parallel simulator, otherwise known as LAMP, and its TTM modfix. Single-pulse laser ablation with nanosecond and femtosecond lasers were simulated, and the ablation behavior between the two were compared. The ablation threshold on the order of 0.1 joules per centimeter squared was successfully reproduced in the simulations, and cold ablation was observed on the femtosecond timescale. But on the nanosecond laser, the lattice maintained its structure, and no ablation was observed at its reported threshold of 5.2 joules per centimeter squared, suggesting hot ablation to be the dominating process of the nanosecond pulse duration regime. A little bit of background on laser ablation. Laser ablation is a process by which one removes material from the surface of a solid by irradiating it with a laser beam. And by using a pulsed laser beam as opposed to a continuous laser beam, we can produce the peak powers needed to irradiate the material. So basically, by taking the energy of a single pulse and squeezing it down to a very short time duration, namely on the order of nanoseconds to femtoseconds, we can create very high powers needed for laser ablation. So a few important applications of laser ablation would be very precise surface etching on materials, and if the metal is under a liquid, it can be used to engage in nanoparticle synthesis, where we have more control over the nanoparticles and its properties, including like size and shape. So there are two types of laser ablation: cold ablation, where the full energy of the laser pulse is deposited to the electrons before the electrons can equilibrate with the lattice. Thus, a large amount of energy is transferred from the electrons to the lattice very suddenly, causing an explosion. On the other hand, hot ablation occurs when the pulse duration is less than the electron-photon relaxation time. So the electrons can equilibrate with the lattice, causing heating and thus leading to vaporization. The electron-photon relaxation time is just the average time between any two scattering events between an electron and a photon just being a lattice vibration. So theoretical works into laser ablation involve two-temperature model, which describes non-equilibrated states of the electronic and lattice subsystem. And the energy transfer between these two subsystems are represented by equation 1, which is a modified heat diffusion equation. Here, CE is the electronic heat capacity, KE is the electronic thermal conductivity, G is the electron-photon coupling factor, which relates the rate at which energy is transferred between the lattice and electrons, and S is just an added source term describing any external energy source, in our case a laser pulse. TE is just the electronic temperature. So methods and computational setup, as I mentioned before, I was using LAMPS and its DTM modfix, which implements the electrons as a sort of background gas on a grid that overlays the lattice, and the energy transfer is described by equation 2, which is a further modified version of equation 1. The new variables here are G sub S, which is electron stopping coupling factor, which was set to 0 for this project because the effects of electron stopping are negligible when it comes to laser ablation simulations, and it's not the main focus of the project. And the S has been modified to a more specific term, better suited for laser pulses. IO here is the absorbed laser intensity, and L sub skin is simply the skin depth, which is related to the wavelength of our laser pulse. And theta x minus x surface is just a heaviside function, so the program knows when our laser pulse hits the surface of the lattice, and our laser pulse in this simulation happens to be traveling in the plus x direction. So one more important thing: the electronic heat capacity was taken to be linear with TE, with a Sommerfeld coefficient of 135 joules per meters cubed per Kelvin cubed. So CE would simply be 135 TE. And I've listed out all my parameters, all the values of the parameters I used. And I calculated a relaxation time around 8 picoseconds, which is reasonable given that the relaxation time for most metals is in the picosecond regime. So for my actual simulation, the simulation box was 100 by 80 by 80 angstroms, and the actual lattice was 60 by 80 by 80 angstroms, and I used a 3 by 3 by 3 electron grid. It was equilibrated at 300 Kelvin under an NVT ensemble and placed in an NVE ensemble right before the TTM model was implemented. And I ran 3 finalized runs, 2 being femtosecond lasers, and 1 being a nanosecond laser, and the parameters are listed there. So results, the first 3 set of pictures are from my femtosecond simulation at 0.1 joules per centimeter squared fluence. So after the laser pulse was finished, after 100 femtoseconds, we can see that not much has changed in the lattice. After 900 femtoseconds, we can see some excitations, and after 1900 femtoseconds, we can see very obvious ablation behavior. On the nanosecond scale, which is the bottom 3 pictures, we can see that I was not able to simulate the full duration of the pulse, which I will explain in the discussion, but we can see that after 2 picoseconds, again, not much has changed with the lattice. After 7 picoseconds, we can see small excitations on the surfaces, and after 10 picoseconds, we can see more jiggling, but the lattice still remains intact and there's no obvious ablation behavior. So at a fluence of 0.01 joules per centimeter squared, no ablation was observed, while at 0.1 ablation was observed, which is very good because it verifies previous experimental data on the ablation threshold of AL being 0.1. And the ablation occurred while the lattice and electrons were non-equilibrated, which means there was a high gap in the temperatures of the 2 subsystems, implying cold ablation was the dominant process in the laser ablation. However, due to my small simulation box and rather small lattice size, the atoms were able to interact with each other even after being ablated, thus causing heating a long time afterward because the ablated atoms were still inside the electron grid. But if the simulation box was bigger and my lattice was more proportional to an actual thin film of aluminum, I believe this would not have occurred. And on the nanosecond laser simulation, no ablation behavior was observed, and the lattice continued to heat up and average around 1100 Kelvin, 10 picoseconds after the start of the laser pulse, while the electrons were at around 1900 Kelvin. And so, although the full pulse couldn't be simulated due to computational restraints, the data does suggest the ablation wouldn't have occurred in a single pulse, and multiple pulses would be needed to engage in hot ablation. But perhaps a more in-depth simulation with a full duration would be needed to make any conclusive statements. In the future, I plan to use my university computing cluster to run more in-depth simulations where I can examine more important details of the simulations, such as ablation crater depth, which is the depth that the crater created when the pulse hits the material, and long-term thermal behavior of the atoms, which I couldn't do here, namely in the nanosecond timescale. I can simulate the full pulse. So acknowledgements, I'd like to thank Jonathan Shi and Professor Say for giving me the opportunity to conduct this research and for the guidance along the way. I am very grateful to them, and thank you for listening.